So we talk about like a special case of like EM and that's basically soft K-mean. Actually, what I described here is like hard K-mean, but soft K-mean will be simple, right? It's essentially the same thing, but then like when you decided the theta 1, theta 2, theta 3, basically the mean and variance, you get each data point you determine the fraction of instead of have a hard membership here, you have a weighted membership. Basically, like this one, for example, like you have let's say according to a mean here. Maybe let's pick this point. If I pick this point here, I compute like the let's see. Okay, I'm not sure I should. Okay, let's just let's say like this one from this cluster here. If like what's the okay, let's compare the likelihood. I guess that's the good one. The likelihood of this guy, like from the mean here, will be just I can call this point exactly is x here, and maybe I will use blue again. So it's x here. Then for this pink one will be just like the likelihood is just exactly this guy here, right? It's just this guy. And then the likelihood for the green cluster will be like maybe there's a theta 1, theta 2, theta 3. Maybe I call this a theta 2 here. This one, maybe this is cluster 1. This is cluster 2. This cluster 3 is what, pink? Oh, light blue, like 3 here. So and then like the likelihood in terms of like cluster 1 will be like x theta 1 here, and in terms of cluster 3 will be like n x theta 3 there. So when we have hard K-mean, this one it's definitely belong to cluster 2, but if we have soft K-mean, the weight for the membership for cluster 2 will be here. I will say the membership is given by so let's say Z here is like the label for the membership. So I mean, if for hard K-mean, I'm not sure it's called hard K-mean, but because the other one is a soft K-mean. So then like C will be just equal to the arc max of like n x theta I, right? Pick the cluster that have the highest likelihood, and then like for soft K-mean.
So why that's like that?
Yes.
So why this should be like hard K-mean should be like this?
Oh, it was just actually this is not completely accurate. Also, I'm lying, but I guess it's easier for me to lie first. But this is like reasonable, right? You just have like for the current theta here, you will just like see which one have the highest likelihood, right?
Oh.
And then you will say, okay, it belongs to that cluster.
Oh yeah, that's
right.
Mm-hmm.
So for the soft K-mean, instead like you have, instead it's like you don't have a PC. It's just a kind of a either 1, 2, or 3. But instead like you have a distribution for C. C is equal to, let's say, I, given the current the mean and variances, will be just equal to n x theta I over the sum, right? Sum of the likelihood. So it just normalized that way, right? It will be a weighted sum. So I said I lie because I to be in practice, remember, like we also, I guess, Benny also mentioned one thing, right? You want to see which cluster is actually bigger, more likely, right?
Yeah.
So there's a weight here. Actually, the weight here is also another estimate along the way. Like W will be like at the current moment, like which cluster you believe is bigger, right? So therefore, like I also should take that into account. So I should have like multiply by WI, something like that. So that's is like for soft K-mean would be like this.
So therefore, this is fractional. This is fraction, not just 1 or 2. This is
yeah, this is a fraction. As I see. Yeah. So for example, like for this point here, maybe it's like 0.7 is cluster 2, like 0.2 is cluster 1, and so on and so forth.
So how to calculate this one? How to calculate this? Mean that how
just sum over them. Like you know this guy here, you know this one here. So each time you iterate, right?
Oh, each one it should be iterate.
Yes.
Oh, okay.
So like you update this theta, and at the same time you update the W. Now how do you update the W? W will be simple, right? W will be basically, let's see.
Oh yeah, how to update W?
You have here maybe I use here WI will be simply let's see, simply the weighted sum of all the C. Maybe I should use another index here. This is I for the data point x. Let's say if I have for data point xj here, this is CJ. That's the label for the j data point here. This is xj here, let's say. And then this is CJ equal to I is XJ. Okay with that, I just add another additional index here. Yeah. So then like the weight update will be like you see like how many data points. Like what's the total fraction of data points that have your membership, right? That's natural, right? So therefore it should be just equal to CJ equal to I theta sum over J.
What is J in there?
Oh, J is like all the data points here.
I mean Z in there.
Z here is the membership or like customer. You estimate what's the each of the data. Okay, CJ is like is the membership of J, the data point J.
So for example, we have a data point in here.
Yeah.
So how to calculate to there? Does it mean that the distance we calculate first?
For example, if I have another point here, let's say I have a. Now if I call this, okay, I use this called xj again. This point is xj now.
Yeah, that's xj.
And then CJ is like the membership of this guy. Whether I think like for hard K-mean, the membership will be just exactly equal to one number.
Yeah.
So it can only be 3 to 1. In this case, it will be just equal to 3 here. And but if for soft K-mean, you will just compare with like each of the likelihood, right? The weighted likelihood. And that's the weighted like. I mean like so you compute, for example, like CJ. You can compute likelihood of xj belong to this cluster 3 will be just equal to this guy, right? It's equal to xj theta 3, right?
Oh, xj theta 3, that is we know that
we know theta, right?
Yeah,
we know theta, right?
We know theta, so we know that
And we weight is like again I will keep updating. We assume that we know weight also. We know W3 here.
But the W3 should be updated in there.
Yes, it's updated in the last iteration. I mean last step we will use the last estimate, right? So each time we will, for example, we have 3 clusters from the beginning. Typically, we will just assume this is 1/3, 1/3, 1/3, right?
Yes.
But then, like as we continue to improve our approximate, this W will change as well.
Will changes by what?
Here, I trying to explain here, but
Oh, yeah.
yes,
Okay.
right. So it will be just, for example, for example, I have what in computing is it? This is W1, right? W1 will be just J. Oh, this is 1 to 3.
1, 2, 3.
Oh no, sorry, not 1 to 3.
1 to all members.
All members, yeah. Let's say
Yeah.
the number of all members. Let's say is just call it n here.
And
Number of data point. So this is sum over all of them.
sum over all of the probability.
Yeah, so this would be the weight. Actually, I probably should normalize that. So therefore, like, I should also have J equal to 1 M P C J equal to I given theta, and
Sigma for all.
actually it's easy to normalize that. Let's see. I think I should just over n or something. Let's see.
Yeah.
I think I should just over n should be fine.
Yeah, that's right.
Yeah.
How to measure P in here? When we know we given theta in here, the theta in there.
But this is from here, right?
Yeah. Oh, from there.
Yes. Yes. So therefore, you update this one. You can update this one, right?
Ah, I
Yes.
see.
Yeah.
Okay. So we find this one, and then we calculate for all of P, WP, WI.
Yeah.
So
Then you can come W1,
Yeah.
W. Oh, okay. That's okay. Yeah, you're right. I use I here. Let's use I here. Let's say for cluster I is equal to 1, 2, 3. 1, 2, 3. Yes.
Yeah, 1, 2, 3, and then we find that that's the weight,
Yes. Maybe I.
updating weight.
Or even better here, like is 1 over n is here. Can erase this. Yes.
But this one is the default one. Default one.
You can start with 1/3, 1/3. Like if you have 3
Yeah.
clusters,
Yeah, 1/3, and will be changed to there.
and then like yeah, after one iteration you change this, right?
Okay.
And then like you can update the mean and variance. So knowing the membership, then you can update the mean, right? The mean will be yeah, it's okay. Like it's simple.
The
Right? The mean
mean
will be just
The mean of cluster.
the mean of the clusters.
Oh yeah, okay, that's right.
The mean of the cluster will be just the weighted sum, right?
Yeah.
Weighted mean, and then like the variance also a weighted variance.
The mean maybe just using first the formula of mean.
The mean.
Formula of mean and the distance then input the distance in there.
I mean like once you have updated this, you can update theta 1, theta 2, theta 3. So
Yeah.
that's basically this, the means and the variance. And the mean, now you know the membership, right? You know the membership of each of these guys here. Then the mean will be just, for example, mu1 will be just equal to PC Cj equal to 1 given your current theta.
But in here there is no update of theta.
No, here I'm updating theta now. Theta has a mu, theta 1 include mu1 and sigma 1, right?
Oh yeah, that's right. Okay.
Yeah. Now here like PCJ, this is my membership, and then I have my, for that point will be have xj, right? Yes, that's xj, and then I will just simply weight the sum with that, right? So j equal to 1 to n.
Oh yeah, that's right.
And let's see, that's the membership. It should sum up to, I don't know, it should sum up to what? Actually, it should sum up to W.
Why it should be 1 in here?
Oh, here I pick 1 here. You can pick I.
Oh, okay.
Let pick I.
Yeah, that's right.
So I do a weighted sum, so therefore it should like that.
That's to make what to
Estimate the new mean.
new mean. That's
Right.
for
And
normalization.
yeah, a new variance will be similar, right? So given that you can, you have this estimate of this mean here, right? Then the variance will be
That's for variance.
yes variance similar I square, let's say.
And that needs normalization.
Yes, I need a normalization also. Right? It will be simply like this. So yeah, then you just keep iterating, right? Then you go back and then compute the membership again,
So
and then update the weight again, and update the
after finish that we find theta 1, theta 2, theta 3, and then also W1, W3
yes.
update. Or after finish.
Yes, after finish, then you know the W. That is basically, then you have the distribution, right? After you finish, you essentially have the weight, the mixture model here. Yeah. And actually, I always get mixed up like which is the M step, which is the E step. So this part is actually the M step, and this is the E step.
So mixed model will be Gaussian and only one. One Gaussian.
What say that again?
After all of them, the step of the finish, that will be mixed Gaussian of this, and we have one Gaussian.
No. Why you see 1 Gaussian? We have like 3 Gaussians here.
Yeah, 3 Gaussian, but if we combine that, we cannot say.
We cannot combine that.
We cannot.
In general, we won't. For example, in this case, you know that after the final kind of iteration, it should converge to 3 clusters like this way.
Yeah, still
One cluster have a mean here, one cluster has mean here, one cluster have means here.
So it's still in 3, cannot.
Yeah, it's just like, no, it won't.
But why in some literature said like if we have something like this, it is 1 and this is 2 Gaussian, so we have both of them will be mean of them.
No, actually, this is an approximation. You would just want to make it, for example, that's the limitation, the difficulty we mentioned like just before the class, before the break. So if you have multiple Gaussians, you a mixture of Gaussians, as you continue to estimate, like you have used number of different observations like this, you need to compare product of mixture of Gaussians, right? So the complexity will just go up. So after a certain point, you may want to group some of the Gaussians together, so to reduce the complexity. So it's just like one of these scenarios. But this one, I don't think is a good approximation. Like if you have 2 like this, it's not really a good mixture of Gaussian to approximate like this.
Why we need to reduce complexity? So what do you want?
Because really the complexity is exponential. If you remember earlier, you have 2 to n. Yeah, if you, for example, like I hope that like next time I will have chance to talk about belief propagation. So actually, okay, there's some logistic also. I think I will still leave an homework this week, but should be relatively short and simple. But I want you to have an exercise for something we talk about, for example, like for Gaussian processor, the stuff like the simple like conditioning, Gaussian conditioning, just do a simple MATLAB exercise. You can just write a simple code, and also like you know that I changed the title of this course to like information theory and probabilistic programming, but unfortunately I don't think I have time for that. Very unlikely. And before before the beginning of this semester, actually I looked into there's a library called Angenica. This is from some faculty member in Stanford. I forgot, like he was in Oxford or like Cambridge. I think it's Oxford. Like then he moved to like UBC, and it's based on Gaussian. It's some programming language.
What is Gaussian?
It's some programming language. Like it's like Java and like, but it's more like Lisp style. If you know, like it's like a variant of Lisp. But
how to spell it? Gaussian?
yeah, it's like Clojure.
Oh.
It is pronounced Gaussian though.
Okay.
Yeah. So I spent some time with that. I spent like actually several weeks on that, like Angelica and Gaussian. But honestly, like I reread it again, like I forget many of the stuffs because like Gaussian is a very different language from what I usually use. Like typically I'm using like MATLAB, Java, and like Python. And I checked with Pyro again. Like I know Pyro is another something like do a inference. This is from by Uber. Yeah, by the company Uber. Yes, and this is based on PyTorch actually. And we look at that. I looked at that like last year. I think it was not very mature, but I look at this again. I think it's like it's quite good now. So what I plan to do is in the homework I would just like ask you just try to run a demo of Pyro or something, like maybe change 1-2 lines there, like very simple. So even though I don't have time in class to really talk about Pyro, then you have a chance to actually look at that.
So why we not use just a MATLAB?
This is actually, if you look at that, like if you have chance to look at that, this is
It's like Python.
It's Python, PyTorch, but more importantly, if it has a whole framework to use to do like inference. So MATLAB in general is not a probabilistic programming language. It is, yeah, you don't you can do some sampling, but you don't do inference directly. Like this guy is basically implement a whole framework like of inference based on what's that called?
There is a toolbook in statistics, so something like R.
Yeah, actually, maybe I'll have something like that, but this is kind of different. Like you can specify like distribution of some variables, and then you specify like what's the observations. Then you can just from that it can derive the evaluate the estimate for you, something like this. But it at this moment is still like not something perfect. Like what I mean is like what we are learning here is not useless still, because like to understand many of this actually like they assume you have like quite a lot of knowledge about the whole inference stuff, like likelihood and so on and so forth. But I think you probably have enough background to just look at some simple examples. So I just look into some very simple, like maybe the hello world kind of example, and just have you guys to maybe change 1-2 variables and have you guys to play with that. Yes, I'll see like if I have chance to talk a little bit more Pyro next time, but I'm not sure actually, honestly. Because there's still several things I have to talk about. Like at least.
So what's the difference between Pyro and Gaussian?
Oh, this actually Gaussian is a general language. The package to do approximate inference is Angelican. It's like based on Gaussian. It's like Pyro is based on PyTorch based on Python. So so therefore like this is actually have like I think it's also pretty nice sometimes, but still like it's for me it's harder to debug because I'm not familiar with Gaussian. Like when there's like trouble coming up, like it's quite difficult. What's wrong? But since like PyTorch and Python is like much more popular, then I guess it's like probably time in terms of like worth spending your time probably like looking into Pyro in the future is like more kind of like useful than Angelican. And so
So it's better if you see that the Pyro and more mastery, more.
yes, that's for example, in my other class, I talk about a variation of autoencoder. I'm not sure how many of you remember that. Like in my neural network class, and they have an implementation in Pyro. It's just like 2 pages of code. So therefore, it's pretty nice. Yeah. And I'm supposing you can do quite a lot of stuff like with that. And so, but you see, like I will probably, I'm not sure I have enough time to put out my homework tonight. If not, maybe like tomorrow I will put out my homework and again.
You will be using that file?
Yes, but it will be very simple. Like I probably just give you a link, just ask you, okay, please just try to run it, like something like yeah. So like, and then maybe just change this variable like to one value, just play with that, like instead of because we don't actually have time to go into detail, but I think like at least you have a chance to run that, like it's very okay. Another nice thing is like super easy to install. It's just like you can like pip install that kind of stuff. It's just a Pyro PL, I think the package name. Yeah, and then you install that, you can run it like immediately. So and they have lots of very good documentation actually. So pretty good. I am not sure how good. Let's see if I have some of these.
So why it's not like something like popular than R Pyro?
I think R is it's a different target. I don't know how in terms of, for example, like really doing machine learning. I'm not sure how many people actually really use R. Yeah.
So this
right.
This is for machine learning.
Yeah, this is like more. It's like also along the line of PyTorch and so on. Right. R is like still like more statisticians use that, but still like more limitation. I guess I'm not sure what's the limitation. Maybe like, I of course I myself is not very familiar with R also, like because of coming from my background, it's not from statistician.
Like many people use
R. Yeah, because they are from
statistics,
right? But I don't know what, like maybe like nowadays people can use R for like machine learning as well, but I don't think they are mainstream in that regard. So and for me, I'm looking more into like if you can deploy stuff like using machine learning, then I think like spend time on, for example, PyTorch and TensorFlow. Actually, PyTorch is really nice. I think it's better than like using R. R probably can do it. Like just you MATLAB, you can do it like for everything, but may not be the best tools for this kind of problems. Yeah. So this is like, for example, like an example of like maybe I would just use this. I ask you to change or something. Very simple things. Like maybe just this one, I will make it a homework problem. Just ask you to make it one and change one line of code or something like that.
Yeah,
So
interesting.
this is have influence, right? Basically, you have a model is like Gaussian, right? You have a gas in this. They use some, I don't know who wrote this documentation. So they try to make it friendly, but this gas is really just a prior. So they estimate the weight, like you're trying to estimate the weight of someone. You have some measurements can have errors, like from the actual weights there, and you have the gases actually the priors, and based on like um, your
So it's really like Python.
yeah, it's
Yeah.
Python because it's based on PyTorch.
Yeah.
PyTorch is based on Python, right?
Yeah, Pyro is library of Python then.
Yeah,
Oh.
Pyro is actually a library of PyTorch. You can think like that.
Oh.
Yeah, because it's based on PyTorch.
Yeah.
So but essentially the main for this one here is trying to do okay. If I have a measure is 9.5, I want to guess the actual weight there. So here, after we spend a couple weeks on a Gaussian distribution, you know that we can compute that exactly. Actually, you can write it down. But this show you like an alternative is that you can use machine to do that. It won't for this kind of problem. Like of course you can hand do it like and you can get an exact solution. And this one it will just trying to do inference using Monte Carlo, and you get something not exact, but pretty close. Something like you get to estimate somewhere. I think I'm not sure it's this one or this one. I think it's this one maybe. This is after you do the
That's minimum square error. What is that?
this is the approximation. I think it's like the approximating was A and B here. Oh, okay. It's approximate the actual. So you have the measurement is like the as I mentioned, you have the initial prior is given by some gas. I don't know what's the exact value here. I think the gas is okay. It's just one here. Wait, it's not given here. The gas is inside. Let's see. You didn't input the gas and okay, gas is here. The gas here, the price is 8.5, and then let's say the observation is 9.5. I think it's 9.5 somewhere.
Yes. Observation 9.5.
Now, then you know that basically we are doing. It's actually very simple. That kind of you have a Gaussian prior that with a prior is a what did I say 9.5 or 8.5 forgot 8.5 8.5 or something.
That is mean?
That's the sorry, that's the estimate. So assuming like so essentially like what we have is like we have the final PDF. Let's say I want to know like what is the true weight here. Is let's say true weight is let me call true weight is W. Let's say here, and then let's say I have the mean here. That is something is the gas here is the prior, and I have the observation there. And
0 or O?
O is observation. Then that's what I want. Now I'm given basically the mean, have a distribution like have okay, P mean here is basically is a Gaussian with 9.5 or 8.5 I forgot 8.5 and range 1, and then like my observation is based on the mean, so I have PO given M. Wait a sec. I'm sorry.
So we want to know W, not O in there.
I want to know W. Yeah, I should know W. Okay, I should given like this. W given M wait. No. O given W is I think it's some wait. O given W. I forgot what is that. I think it's 9.5. It's assuming the mean is W there, and it's 9.5. No. What is 9.5? Now I can't forget.
Observation.
Oh, okay. Observation is 9.5. I'm sorry. So this eventually will be 9.5. Okay, but the distribution for this guy is a mean is W. I think variance probably is 1 again. This is given. And what's W? Okay, W. This is the Pyro. Pi is distributed like this.
How to get W from there?
Oh, actually, I don't have really need a mean here.
Use variation.
I don't even need that. I probably don't even need that. I actually have PW given by this. PW is given by that, right?
W.
Yeah.
Oh, okay. That's
Yeah, this is a pretty simple problem here. So it's the sense we just need to multiply them.
So what we want to get from them? Or
We want to get W. O now is given by 9.5. This is 9.5 here.
Okay.
So we want to get W,
W.
right? PW, given observation basically.
Oh.
Yeah. Or you first you can then this is basically PWO
Yeah.
over PO something like that.
Oh yeah. We should find EO first.
Yeah. And we can find actually we don't actually need that. If we want to estimate W, we can just O is given. O we know what is that actually.
How? We don't.
Oh, we say O is 9.5, right?
Oh yeah, 9.5. Oh, 9.5. That's mean.
Yeah. What I mean is like we don't need this for estimating W. We want to maximize. Essentially, we want to maximize W, right?
Oh.
Maximize this probability for W. So this is a map estimator. So then we just multiply this. Of course, the maximum will be just the mean here. So we multiply this. It's just what we did earlier, right? So we have the multiple is equal to 9. I think it's not 1 here because otherwise it would be equal to 9. I think it's a 9.1 something. So let me see like what is the variance here. Oh yeah, you say like 0.75.
Oh yeah. There's the case and weight in there. Measurement case and weight.
Yeah, but actually it's true. But as you can see, how it is written down is a what is that? It's actually Markov, right? It didn't depend on gas here. Yeah, he only depends on the weight here. Yeah. So but this is 7.5. 0.75 is at here, right? 0.75.
0.75. Yeah, we know that.
So then like, okay, that we can do this exercise again. What's this multiple? This multiple is W. Is the weighted sum of these two, right? But it's like weighted by the position, right? This is 0.75. This is 1. So therefore, it's like it should be 9.5 times 1 over 0.75, right?
Why 9.5?
Here, always assumed to be 9.5.
Oh yeah.
And then like plus 8.5 times 1 over 0.75 plus 1 over 0.75. 1 over 0.75 plus 1, right? Hopefully, I believe this is equal to 9.1 something. That's what they get, 9.1 something approximately.
That's for mean.
Yes, the mean.
Oh.
And then we can even know the variance, right? The variance is equal to
No, variance, that's add each other.
yeah, it's equal to sum of the precision.
Yeah,
So therefore, it's equal to 1 over 0.575 plus 1. And take 1 over is the variance.
Yes, that's variance.
And we even know what's the weight there.
Yeah.
And the weight is basically the difference between 9.5 and 8.5, right?
Yeah.
And the variance is like sum of them is 1.75.
The variance, yeah.
Yeah. So that's what I mean. Is like you don't even need to care about this because this is exactly this guy, right? Yeah.
Already there.
Yeah. I mean, like this. If you want to find the P W kind of given O here, this multiplied by this is proportional to. It's actually this multiplied by this is equal to PWO, right?
Yeah, PWO.
And so therefore, this is actually equal to PO, and this is actually equal to PW given O, right?
Yeah.
Yeah.
That's the PW.
Yeah.
Okay, so how to get this maximum?
The maximum is the mean, right? Because it's a Gaussian distribution.
Oh yeah.
Yeah. The maximum will be simply the mean.
The mean from where?
So therefore, it's 9.1, right?
9.1.
For this guy, the maximum is just the mean,
yeah.
right? Yeah.
But we also use this. This one will be maximized. W.
This is a constant, though. It does not depend on W.
Oh yeah, this is constant.
Yeah.
We didn't depend on W. It's just only this one.
Yeah.
And the maximum in the mean. Oh,
yeah, maximum is just the mean. So therefore, you see, like, knowing this multi-product is nice. You get something exact very quickly.
Yeah. And how machine can do that?
And the machine, okay, it don't know how to do this. It doesn't know how to do this equation. So instead, it will do a
And then the same, the result same.
The result is close. So it have 9.1 something. Like this is the exact. It's 9.1 something. Like you do some iteration, you get here.
But why is something like should be done using iteration, the calculation?
Because here is something like similar to EM also. It's
using EM.
Not exactly EM. Actually, but similar principle that you cannot maybe next time we can talk more about that. But like here on high level, what it's doing is like you will have difficulty trying to what should I say? Wait a sec. I want to sneeze. So the problem here is they won't be able to, like, of course the approach is using here is like more general because I can do it like by hand just because I'm playing with Gaussian distribution. So I know exactly the equation that okay, when I multiply these guys here I will get the solution like that. But in general, like it's not easy to compute this and then try to maximize that. So you will need to do something like EM, right? Then yes, you will try to instead of sometimes you may not even able to write this down exactly. So what they do instead is like they try to have a so-called guide function. In Pyro they call it a guide function. It's like they have an estimate of this guy just estimate with something else, a QW, or with some parameters here. I don't know what kind of parameter to use. Maybe I call it A something. And what I'm going to do is you want to fit this with this guy here. Sorry, I mean you may not be even able to write down this. Here it's very easy for me to write down because it's Gaussian, but in practice often you cannot even write down this precisely.
Okay.
So what we are going to do is 2 steps. So we will have another distribution trying to pretend to this one to make it close to this one. So I want to create another distribution. And this distribution doesn't necessarily is exactly to this, but I hope these 2 guys to be similar.
Okay.
But how I can play with this guy because this distribution is have a simpler form, and I can parameterize this with some variables. For example, in this case, I can have the distribution is simply again a Gaussian. So I can have a Gaussian again with W, with some mean and variance here. But now I don't know what is this guy here. In this case, I'm lucky. This is actually Gaussian, so I can have an exact A and B will fit this completely. But in general, I can still use something like whatever stuff trying to fit this guy with this guy. So then I have split this problem into 2 different problems here. So it's a little bit, therefore I say it's a little bit like EM. So I'm trying to make this guy close to this guy here.
Yeah, that's right.
And then at the same time, this is one iteration step. And at another iteration step, I try to maximize this guy with a step to W.
Yeah.
So then I have 2 iterations. So therefore, you see the become an iterative part. Yeah. So at one time, it's trying to estimate this
The
value.
and
So
one-
actually, this is AB is exactly try to parameterize the distribution and using another Gaussian to estimate the posterior. And then they estimate that distribution, the end up the estimate will be this A and B, right? And once you have this estimated distribution, in this case very simple because the maximum will be simply the mean, right? So then therefore the maximum is just A there. Just the A there. I mean once you have this approximate distribution, you want to find the maximum for that distribution is simply at the mean there. If this is a Gaussian. So, but this is basically called a variational inference. Maybe next time I'll elaborate more. But
yeah, how to get close to the you mentioned? Could you go to the your
oh, okay. I guess I better come back next time because I was not prepared for that. So
yeah, that's the algorithm.
yeah, that's
how to get there
Yeah.
to make it close to PW given O. Yeah.
yeah.
Okay.
So, but basically, using Pyro is kind of automatic. So what they do is you just need to specify the guide function. So what kind of guide function you're going to use here, right? And then okay, you define what is that guide function there, and then you just kind of make it automatic. They will try to maximize. Find make this one close to this one, and at the same time they're trying to maximize this guy. So
But if I saw in the code, maybe you can see the code. That's something like you use the this one momentum SGT. Yeah.
yes. That's the optimization here.
Optimization.
They use because we need to approximate that you need to make that 2 distribution close, right? So then that would be a score to compute how close the 2 distributions. Then you try to optimize that. Therefore, you need to have a user optimization package to just
Gradient descent
Yeah.
to make close to that
Yeah.
optimization. So that's the core for that to find that.
oh yeah. You just call the package like in PyTorch. You don't implement that. You just specify what kind of optimizer you're going to use.
where we can find this one? Okay. This is a IPMD. This is a notebook.
Oh, this notebook. Okay, this is just a that documentation have that. So
Oh, so
they have
you-
lots of but okay. Oh, oops, did I stop the video? Did I? Okay, I think maybe I stopped the video just for a moment.
Okay.
Okay.
Yeah, from where that we can find that?
Wait, did I start the? Okay, shoot, I didn't start the. Did I start the screencast at all?
You stop that?
Did I start it? Okay. I have it. I just worried I didn't start it. So yes.
From where we can find that?
Yes. From there, Pyro. You just look for Pyro. Pyro. Yeah, Pyro. Yeah, you search Pyro like it.
Oh,
Like,
I see.
yeah, I think this is the first
Find
introduction.
that. Okay. I
Yeah,
understand.
and this notebook you can download that. Like there's page source. So then you can just save it as a
Yes.
Jupyter notebook. Then you can run it.
Yeah. In the virtual environment.
Yeah.
Okay.
So I probably would just use that as an example. I asked you change maybe from 9.5 to 10 or something. Then like just run it again. So
So it means that if we know there's no need to write the math anymore.
no, actually, the knowledge is still useful because
Yeah, of course.
the inside there, like they mention lots of this. They assume you know some of this stuff. For example,
Yeah.
elbow, like they assume you know lots of stuff. So to have a better kind of
It's something like to know something like to calculate the Quebec lever. That's right. Because you
yeah,
have
yes,
this
actually
division.
they have a KL divergence also.
Yeah,
Like
yeah,
actually the elbow like is kind of related to the KL divergence also.
Mhm.
And
To find the close of the
yes,
distribution.
okay. I guess like yeah, that's good. So I'll leave this as a homework assignment to you guys. Maybe next time like we'll talk a little bit more about this. I don't know what. Yeah, actually, there's a lot
I'm
to
still
talk
a
about.
little bit quite don't understand about the when in your
Yeah.
presentation. Not bad.
No,
In the
yes.
presentation. In your top, yeah.
Yeah.
This one 9.5 and this is actually the mean.
That's an observation.
This is the mean.
Depends on how to look at that, right? This is a PO times PO given W multiplied by PW, right? It's
Yes, that's right.
the observation is already given now. Is equal to 9.5, right?
Oh, this is not mean. This is not in here, but in here in O.
Yeah, but you can move it around, right? It doesn't matter because for the Gaussian distribution, like I write like this O mean as W 0.75. The function will be the same as a WO 0.75. It's symmetric.
Oh,
Yeah.
okay, that's right. And then
Yeah.
the O is our data. We know that. Also.
Yeah, that's when we know that. Already know that.
Okay, that's right. So that we know we want to find the W because we already know O in there, and
Yes.
we want to find the W. So this W, and this we know this mean, and this is variance.
Mm-hmm.
Yeah, and find that. So that's, yeah, this one W to maximize that. That's what we want.
Yeah.
The complexity, if there is not only one, if more than one, something like that.
You mean like if it's a mixture of Gaussian? Yeah.
Yeah, I mean that for when we should use the Pyro, maybe if there is some complexity here.
Yeah, if it's not Gaussian, like Yeah, probably. There are lots of example usage. If you can look into that, and
Yeah.
I would just say give the simplest one as this one as a homework calculator for you guys to play with that.
We can use this also to this project.
Yes, actually you can.
Yeah, it's because I want to get the Gaussian. Yeah.
Yeah. So I guess okay, for the rest of the time I want to keep a little bit more general form of EM here. Here we talk about a specific application for soft. Actually, I didn't even derive why we are doing that. I just give a intuition this should be the way that supposed to go, but EM is more general, in the sense that the original problem is trying to target this way, and this doesn't necessarily to be mixture of Gaussian, can be anything. But essentially, the difficulties is again you have this expression itself is not easy to write it down, basically. So let's see. Let me start a new page here. So again, we're trying to. Oops. Never mind. We are trying to maximize this P is given theta, maximize over theta, and so first thing first. So we'll try to see if we can add some helper variables. In our previous case, for mixture of Gaussian, the helper variables this C here is the membership, right? So assuming essentially we for other problems again if we can put in some helper variables as you see here, so this I can rewrite this as a PC given theta and sum over C, right?
Why there's Z in there?
So this is just something it's a helper variables. So in the sense it's difficult to write this down directly or optimize this directly, but instead if I have, for example, in our previous case here, it's difficult to we know the theta is this one, and this one, but we also have this W1, W2, W3 here. But it's hard to optimize. Okay, in that case we can write this down, but it's very hard to optimize this directly. So therefore we introduce some helper variables C here. I mean, in our case here, the C is basically the membership, for the mixture of Gaussian. But in general, it can be something else. For some other problems, it can be something else. But let's say I have a Z here. I'm also if I, instead of maximizing this, I try to maximize the log instead. It's essentially the same thing. Yes. And then if I maximize that, I can also rewrite this as log sum over C QC given X. So again, I add something dummy here. This is something dummy, right?
Okay.
Yeah, this is something dummy. But this thing if we get back to the mixture of Gaussian case, so this thing is for each of data points, I want to see what's the membership for each of this guy here, the probability of membership here. But once I do this, I can use Jensen inequality. I can say that this is larger than equal to sum over Q C given X log P XC theta QC given X C. So this is larger than that. So instead of maximizing this guy, I can maximize this guy instead.
strength equality.
Yes, this is just strength inequalities.
So you put that in here, so log in there. So
Yeah.
this is all
Yeah, because a log is a convex function, so it's just strength inequality. I can get into that inside.
Okay.
But you see essentially what we are doing is that like if EM basically is just this is actually the end of EM. If you want to so the main idea is just here. So instead of like maximizing this guy, we are actually maximizing a lower bound.
Okay.
So we are maximizing a lower bound here.
Maximizing lower bound to go there.
Yeah. Instead of maximizing, actually we are actually essentially maximizing this.
Yes. Okay. Maximizing that.
And
So equal to that. This one will be equal to that. To this.
actually it's not necessary. So therefore, like in the sense like the solution itself doesn't necessary to be perfect as well. Like even though it's very reasonable, especially for the Gaussian mixture case, but in general, like we are really maximizing a lower bound instead of maximizing the original likelihood. Yeah, and we can kind of like look more detail. Like I mean, what's the gap between these two guys here? Basic. I'm also like, by the way, I want to point out that there's a name for this guy.
That's QL.
Huh?
Oh no, not that is QL.
Q.
Cubic fiber. QL. No.
Oh no, it's not really. If you remember, the KL is a
It's different.
is a this should be above, like basically.
Yeah, it should be above. Yeah.
So this has a name for that. Like I'll just specify this as FQ theta for now here. I'm actually sometimes in physics it's referred to as the negative free energy. I don't know what kind of free energy, but it's some kind of free energy.
That's like.
And then like, by the way, like if we look at this FQ theta here.
FQ theta is mean that for all
This
of
guy.
this? All of this?
Yes, the whole thing, this whole thing,
whole
whole thing, FQ theta is the whole thing here.
Oh.
I can write this as like QC x log p x c theta. I can just split that, so minus QC x log QCX, and let's see. Oh, by the way, why I write this? I don't know why my notes add that. This is useless. So, let's see. Instead, I want to split this. Split this one into P C given x theta times P x given theta. I mean, just this guy split that. PC given x theta, P x given theta over QC given x. And so I can split that. This one is equal to minus ZQX given, QC given x log QC given x. Yes, this is C and x. I'm sorry. My handwriting is too bad.
This means this is Z?
Yeah, sorry. Yes, this is C. This is x. C is x. Yeah, this is so. Yes, this is a minus of that. Let me put that PC given x theta here. So this guy I put it here. And I have one more term here is like sum over QC given X log P is given theta.
Why this is minus and this is become above, below?
Mm-hmm.
Oh yeah, minus in here, so this will become there and then become there. Oh yeah, that's right.
Yes. Well, you look at this, okay, this is just come back to our log Px given theta here, right? Because it's like, this is independent of C, I can pull it out. This sum over C, this is distribution. So it's sum over to 1, so I just have log Px given theta here.
Why? This one is C? So
Yeah, Pc given X here.
X. So it become 1, this one?
Yeah. This does not depend on C, right? So therefore I can pull out from this sum.
Okay.
So this is just sum over to 1.
Yeah, it's more 1.
Okay, this is what originally we want. So the one left here, if you look at this, it's just the KL divergence, right? Between Q, C, X. This is minus the KL divergence. And P, C given X theta.
Yeah, that's right.
So if you, okay, so if you look at this, okay, this also specifies what is the gap of our lower bound here from this original one here. So the gap is basically the KL divergence.
Yeah.
So if
that is 0, so it's
if this 0, then there's a good estimate.
Yeah, maximum. A good estimate. How to make that 0? It should be same. This one and this one.
So yeah, it should be the same,
Yeah.
but it doesn't necessarily. It's easy to be the same. So let's think back to our Gaussian mixture example. So the QC set X is like the membership, right? Basically, we want to have the membership is reached to the true membership, basically.
That is the true membership.
Yes, if this is a true membership, then will go to 0.
Yeah.
And then that would be nice. Actually, therefore in the Gaussian mixture model probably is okay. For example, for our previous example there, if you agree that like this is actually have three clusters like that, and this is actually the true membership, then it is actually have a pretty good estimate of the original likelihood, because then the KL divergence that specified in here should be pretty small.
Oh, so it means that this is the true membership, and this is the true.
This is a true membership. This is the PC given X theta is the ground truth there.
Ground truth.
And this is something you keep on estimating.
Why this is ground truth?
Oh, why this is ground truth?
Can you go back to the above? This is ground truth. What PXZ given theta?
I can only say like this is fake. Like Q is like we introduce as something like okay, this is dummy, right? It can be anything here. We introduce dummy. This is a something like start.
Oh
yeah.
Right. Yeah, this is dummy. You mentioned before.
Yeah, this is the dummy, and then we hope this dummy is like actually in the Gaussian mixture model is our estimate membership, and we hope this estimate membership is close to the true membership. If that is the case, then this will be equal to 0, and then we really have the free energy here.
Yeah.
I mean, this term is exactly equal to the likelihood. So then the EM the general EM algorithm is really just iterative algorithm, because basically you have like Q and theta here. You just each time, for one time you try to estimate the Q, like maximize the F in terms of Q, while theta is fixed. And for the other step, we just do the reverse, like keeping like Q fixed and then maximize theta. So precisely the E step is the one that I'm trying to maximize.
Maximize Q first.
Q with theta fixed. So
Okay.
basically, this one you're trying to find the best membership there, if a Gaussian matrix case. And then like for the M step there is trying to find the mean and variance basically. I'm trying to do something like that. So that's the general EM algorithm.
For the second step,
Mm-hmm.
you this is the fix now.
Yes,
The Q fix. And
Q is
then-
fixed with the previous
and
step.
Theta is step.
Yeah.
So this one, and then second one, and then go back again.
Yes, yes,
This
yes.
one.
Just
Okay.
keep iterating.
So how to make that? To make that?
It depends on the problem then, right? Because
For example, theta become x fixed, and then Q maximizing, and then but maybe after we have now this Q and we become to there. Yes, if we already have this one, so this Q will become to here, and this is
yes,
Q.
yes, yes. Then we'll come to here yet. And I can say a little bit more, elaborate a little bit more, but I guess I will end there. So for F again is basically, therefore we have like is wait a sec.
This is something like I can do also in the to maximize in the Bible concept.
Yeah, actually, this is it's very general. I'm sure like you can use it for lots of places. That's why like EM has been invented like in many disciplines. So remember that like I have this FQ theta. I can write it as this form, right? This is equal to maybe more precise FQ to theta t, FPC given x theta t plus log p is given theta t. So now for the E step here, if I try to maximize over Q there, so if you look at this guy, this side here, sorry for my handwriting, this does not depend on Q, so I can ignore this, right? I don't need to care about this. And for this guy here, it would be very simple, right? To maximize this guy would be minimize this K divergence.
Yes.
So therefore, like the optimum Q is just equal to, so Qt plus 1, C given X is just equal to the current PC given X and theta T.
Oh yeah, to make it
Simply
same.
that, yes, make it the same, just simply that. And then like for the M step, this is the E step actually. E step.
But that is for Q, so we should update the Q in there. Therefore, you T plus 1 and then that's right.
Yeah, Qt plus P plus 1, yes.
So update Q.
Yes, the T plus 1 will be that. And then like M step, so I should max the theta this time.
Why you call that M?
Oh, they don't ask me. Like, this is very annoying. I keep forgetting that, right? Because this is kind of history I'm not really good at.
Oh, okay.
Yeah. To me, like both of them is maximization. I don't know why they. Probably like historically, there's someone derived in another way.
Yeah.
Yeah. So, but I have this. Yeah, for this guy I can write in for this one I will write in another form. Remember, like this is actually just equal to this one here, and I can write it as this. I can write this. Okay, this original this guy I can write it as a p q c given x p x c given theta minus c q c given x. Wait.
No.
My log is inside actually. My log is inside. I'm looking at this term here, not this one. This is original likelihood. We are trying to maximize this lower bound here. So, and log QC given x. So when we're trying to maximize theta, then this guy is redundant now. We don't care about that. Actually, this is an entropy. We don't care about. We're only trying to maximize this. So for this maximum step will be equal to. Actually, we cannot. In general, we cannot kind of simplify further. It's simply like that. Qt plus 1 c given x. Where is that?
Why? So because there is z in there.
Log px c given theta. Basically this. We cannot. So for the e step we have simple like this, but the m step we cannot do much more.
I don't get this. From where is it?
That is the original one. We're trying to maximize this actually.
Maximize it. Q.
Yeah, maximize this. Remember, this is the one we want to maximize. That's the fq theta. Just what I did is this because the this equal to this guy minus sum over qt plus 1 c given x log qc given x.
Yes.
And this term does not depend on theta, so we can ignore that.
You didn't include that.
Yeah.
Oh, yeah, that's fine.
So that.
So just maximize this.
Yes, just maximize this.
Okay. That's right. So why in here should be sum on there? Summation.
We need that. Yeah, we need that.
You need that.
Mm.
Do we sum all of them? Oh yeah, that's right.
Remember, like this is where we, for example, like when we compute the for the mixture Gaussian, we have the update for the weights and update for the mean and update for the variance is exactly like this, right? The weight is like the weighted sum of this guy, right? By that estimate xj there, that's the yeah, of course here I'm kind of jumping step there, like I'm trying to maximize that. I mean, if I try to maximize these guys, if then you can. Okay, maybe I go one more step, like to show you if I try to maximize this. Great.
Because that is the KL in simulation.
The KL is gone. Okay, for the M step here is just this guy. Because again, like originally, we are trying to maximize this guy over theta, right?
Yes, over theta.
But the denominator here does not depend on theta,
Yes.
so therefore we just erase that.
But on the original KL, there is sigma summation. Original KL, there is summation. That's right.
Yes, we have that. The original we have that.
So
This is the one here.
So therefore, we still need this one, even this one disappears.
Yeah. We have this guy. We originally have this, right?
Yeah.
We always have this guy. But what I'm saying, like for the Gaussian mixture model, then we can go further. Like for example, like this I know what is the pxz theta, right?
Yes.
This basically like if is equal to sum over this is kind of
That's right.
so that one is actually this one, if I have a Gaussian mixture, this one is a Gaussian mixture model, right? So so this is actually equal to W1, in our case is W1 kind of like X theta 1, W2 X theta 2. Yeah, there's a C here, is the membership there.
That's not the Z. W1.
Yeah, yes. Let me get. Yes, you're right. I only have one term here, right?
Yeah.
So for one of the C, so yeah. So that is when C is equal to 1. So I sum over C is 1, 2, 3 basically, right? So let's say it's a C1 here. So then I log this guy here, right? Log this guy. So actually this should be like Q1 given X, let's say something like plus Q2 given X log W2 theta 2. Let me just like write Q1, Q2, Q3. W2 and X theta 3. Now I can write this in the Gaussian form, will be like exponential minus 1/2 x minus mu 1 square over sigma 1 square, let's say. Right?
Theta actually there is mean, mu, and
yes, the theta will include actually both mean and variance. So I just for convenience I write theta 1, theta 2, theta 3.
yes,
But in this day it should be like mu 1 and sigma 1 square. Now then you can take, I won't go into it because we already running out of time, but you can do it as an exercise. Then if you try to take partial derivative with respect to this, will be your objective function, basically like this. And you can take partial derivative with respect to mu, for example, mu 1, and set it to 0. Then you compute that, it should give you back to this kind of equations here. Yeah, and then
okay. So finally you find that
you can
using Lagrange using KKT.
Yeah.
Okay.
So, but I will just stop here. Like I won't go into that further. But yeah, I guess next time, last class I don't know. I may not be enough
So
time.
after that we find mu and also variance.
Yes, you can find mu, the update mean, and the update variance, and update W as well.
Yeah.
And then that if we take the derivative set to 0, if we have all the calculations correctly, then it should get back like what we have earlier. So okay, I will just stop here. Like okay, I will see you guys next week.